Hello everyone and welcome. Thank you so much for joining us for today's webinar on mechanical control of moisture in cultural heritage settings. You may have also tuned in for a program that Jeremy gave last month on managing moisture in non-mechanized environments and disaster situations. You can check out the recording to that in the chat box on your left-hand side of the screen. I've just included a link to the program from last month. My name is Jessica Unger, and I am the Emergency Programs Coordinator at the Foundation of the American Institute for Conservation. I will be serving as technical support for today's program, and I am happy to address any questions you may have. Today's webinar has been organized by the American Institute for Conservation's Emergency Committee. The Emergency Committee aims to promote awareness and increase knowledge of the AIC membership in the areas of emergency preparedness, response, and recovery for cultural heritage. Thank you to all of the committee members who have worked to make this program possible, particularly the committee co-chairs Becca Kennedy and Howard Wellman, and Chair Emeritus Katie Wagner. Before we begin the program, I wanted to share some technical notes. On your screen, you'll see several boxes, including one labeled chat there on the left-hand side. I think you all have found that by now. You can, of course, use that chat box to say hello to each other, to ask questions, and also to share any information you'd like. So you'll see from the link that I shared with the recording to last month's program, the links are live, so it's a really great way to easily provide resources to others. If you post a question in the chat box, you'll receive a written response from me. Any questions will be noted, collected, and then I will verbally ask them of our presenter at the conclusion of his presentation. This program is being recorded, and it will be hosted on AIC's YouTube channel. All registrants will receive an email with a link to the recording as well. And with that, I'm very pleased to introduce you all to today's presenter. Jeremy Linden has been the principal and owner of Linden Preservation Services Incorporated since 2017. He is an active educator and consultant with 2 decades of experience in the cultural field, the last 8 years of which have been focused on enhancing preservation environments and sustainability. He has taught and consulted for institutions around the world, has been a pioneering researcher on methods and strategies to reduce energy consumption in preservation settings, and is an active participant on national and international standards committees. His passion is helping institutions preserve their collections in the safest, most economical, and environmentally responsible way possible, finding solutions appropriate to individual buildings in diverse climates and geographic regions. And with that, I'm very pleased to turn things over to Jeremy.
Okay, hi everybody. I hope you can hear me. If we have any problems with the audio, please do just write in, let us know, and we'll make some quick adjustments. But welcome to the second round here, if you will, of what we're going to do for moisture control and thinking about cultural heritage. For those of you that were joining us last month, thanks a ton, and hopefully a bunch of you have come back. For anybody who's new with us this month to talk about mechanical control for moisture, thanks for joining in. We're going to go through some things today. I'm going to warn you off the bat that this is kind of an introductory overview session. I don't get into a lot into the technical details, but we'll talk about processes and how it is primarily that we think about moisture in cultural heritage settings. We talked a lot last time about going through and thinking of where the moisture comes from and what our goals are, what the particular concerns might be, what ranges we might want to think about in terms of where risk occurs. For this time, we're really going to talk about what can we do. In other words, how can we go in and have an active role in removing that moisture from an environment by means of mechanical intervention. So to go through and just to get started. And first of all, let me just say today that I am joining you from the West Coast today. I'm out in Seattle, Washington. So for those of you that I'm seeing checking in, thanks for joining. I know I'm in your backyard for a few of you. And for other folks, thanks a lot for joining in. I see some folks from Spain and Brazil and a couple other places throughout the Caribbean. I'm glad you could come in, and I want to make sure today that we go through it, and I'm going to do the best that I can to cover some information that's going to apply to everyone. We'll get a little bit to the disaster response stage of this toward the end, and my goal is really for that to be something of a discussion, because I think when it comes to mechanical systems, this is truly, shall we say, a developing discipline. We knew a lot in the past. We had a specific response. Recent disasters, recent issues throughout the southern U.S., throughout the Caribbean and Puerto Rico in particular, have, at least in my mind, really made it so that we need to rethink some of those approaches. So I do want to talk about that, and I will say, please do send in your questions toward the end here. Jess is going to shoot them over to me when we're ready. And with that, let's get started. So as I said, last time, about a month or so ago, we started talking about where the moisture comes from, how it gets into the building. And now we're going to approach that for this concept of what is it that we can do about it. It's not just about the envelope today. We're going to talk very briefly about the envelope, but we're really going to move into that mechanical control perspective. We'll go through some of the typical equipment that you might see out in the field. And I'm going to preface this by saying that I've really focused on equipment and processes that are designed specifically for moisture control, which is to say that I don't have a lot in here today for the sake of temperature control or straight up air conditioning. We can talk about that near the end. I'll pull that into play a little bit so that we have that perspective. But this session is really about moisture control, and it is a different mechanical process when we think about that from a building intervention or from a mechanical system perspective. There's a part in here in terms of thinking about what might be appropriate for my particular building. And this is something that we'll approach kind of broadly between historic and, shall we say, modern envelopes. As I said, we'll touch on this a little bit. But please do understand that the examples of systems that I'm going to put out there are truly case-by-case, shall we say, application in terms of thinking about what geographic regions they should be used in, what type of weather conditions, what type of building structures. So there is no one-size-fits-all when it comes to mechanical control or mechanical intervention for moisture. And I think as we look at that and as we go through today, it'll start to become a little bit more clear that when you're looking at your own individual setting, when you're looking at your own individual building, you really do need to consider what your primary concerns are, where the moisture is coming from, and in your case, for the building, what is the best approach or what is the most reasonable approach to trying to have some mechanical intervention for moisture control. And finally, as I said, toward the end, we're going to spend a few minutes and talk about what to do when we do have a disaster situation when it comes down to equipment. Oftentimes in the past, the immediate response kind of turns to, well, let's either turn on the generator or make sure we get a generator. And I think it goes well beyond that. And I want to make sure that we have a bit of a discussion there. So we talked last time about the difference between moisture management and moisture control. And when we were talking about envelopes and specifically, shall we say, historic envelopes, really structures that were meant to breathe, right? That were meant to allow air to come in and out, that were meant to allow moisture flow, temperature differentiation throughout the day and the night. We were talking about the aspect of thinking of it as a management perspective, that we couldn't actually control moisture as such, but that we could help direct the flow, that we could allow the building to behave the way that it was originally designed to. As we talk about mechanized environments today, we're really talking about actually going in and specifically intervening and creating a control scenario over the environmental conditions that we want to change. Now, we're very used to doing that in terms of temperature, and it's fairly straightforward. We either heat up the air, we cool the air down. But when we're talking about moisture control and system design for moisture control, this is entirely different because we're looking at a level of work, oftentimes a level of energy, that standard temperature control systems, i.e. your typical furnace, your typical air conditioning system, are simply not designed to do. So we're talking about moisture control in this aspect and what the specific equipment or what specific designs it requires in order to have that ability to either remove moisture from the system or for dry environments or cold environments to add some moisture into the system. So this is a world where control is possible. It really does depend, though, on the equipment and the controls programming that we have. Oftentimes, we have a lot of discussions going through of institutions that have a certain type of equipment and for institutions that have a certain installation and are looking and going, why can't we do better when it comes to moisture control? And the answer oftentimes comes down to simply the capability and the design intent of the system that you're working with. If the idea for moisture control was there from the outset and it was built into the system, then we likely have some flexibility and some opportunity to go in and change what it is that you're doing for moisture control. But for many systems where the original intent was really about controlling the interior temperature, making it a little bit warmer in wintertime or in cold seasons, making it a little bit cooler in summertime or in hot seasons, then the moisture aspect or the capacity of the system to pull that additional moisture energy out of the air could be very, very limited. And we'll talk about that and touch on that just a little bit, especially with different types of systems. And then finally, this aspect of, hey, we can control moisture if we have mechanical equipment. Well, it's obviously not quite that simple. When we go through, we understand that there are many scenarios where, even though in a perfect world, we can exert mechanical intervention over incoming air, over moisture, and control that moisture content to make it what we want it. If a disaster strikes, if we have a tornado, if we have a power outage, if there's a flood, if there's a hurricane, any number of possibilities as we look at this, let alone maintenance issues and equipment breakdowns. All of a sudden, what the control that we had presumed to have, that we had walked into this scenario recognizing that this is what we're able to do, and that my preservation condition depends on that, all of a sudden we lose that control. And how is it that we respond? How quickly might things go bad? How do we have to think about that moving forward? So before we kick off the true mechanized portion of this, if you will, and please note that that doesn't mean that I'm going to pop a computer on here to talk to you, although that might be fascinating in the future. A few questions that I got from last month. First of all, thanks a lot, everybody, for all of the evaluations and all the comments that you sent in. They are very helpful, and we do, both Jess and I do review those in order to figure out what we can do to make things better this time around. But also to a few of you who wrote in to me personally in terms of just getting in touch via email. There were some really great questions throughout all of those, and I want to touch on three of them here quickly because I think they're things that really do impact everyone, and I think many of us have probably run into this situation at some point in our careers. So the first question was specifically, how is it that we can gauge, how is it that we can sort of physically recognize or understand what the moisture content of the dew point in the space might be? The specific question is there in the first bullet point, and it's really talking about this concept that we recognize when we walk into a space that we can feel temperature. Our bodies are pretty well attuned to that, although everyone is, shall we say, calibrated slightly differently. What might feel warm to one person may feel a little bit cool to another. But we are fairly good at differentiating, shall we say, movement and temperature and understanding when it's either heating up or cooling down, regardless of what that means for us on a comfort level. Moisture is much more difficult. It can be relatively hard if you haven't experienced and actually looked at different relative humidity conditions in a room. It can be relatively hard to walk into a space and have a feel for what that relative humidity or moisture content might be right off the bat. Our bodies are not, shall we say, a good barometer for that, if you will. So what we need to keep in mind is what is it that we can sense. And I think we've all walked into a space before, or even outdoors, where we've walked out, say, on a foggy morning and gone, ooh, it feels a little bit clammy, or a little bit damp, or it's an extremely humid day. And those senses that we get when we walk outdoors, I know it's been really tough in the Northeast U.S. this past month or so, or this past couple of weeks in particular, in terms of particularly humid weather. That same feeling can really bear well or can really help us out when we walk indoors as well. If we walk into a space and you get that feeling of it's awfully humid or it feels kind of clammy in here, if it's cold and damp, absolutely take that as an indicator that the moisture content may be off slightly. What you're actually sensing is the relative humidity, not the specific moisture content. But that in and of itself, that indication that the relative humidity might feel high, is something that is worth then going and trying to track down information for what the actual measure might be. And for smaller institutions on up to larger institutions, there are a lot of ways that we can really sort of get in with that initial measurement of what might be going on. I oftentimes get questions from smaller institutions that are, shall we say, having a rough time getting into environmental data logging, or how is it that we afford the equipment? What can we do? And the idea behind that, and I hope none of us have really taught to the contrary in the past, or at least not intending to, is not to make that an exclusive situation. I think there is a real value in terms of even just basic hygrometers, basic equipment going in getting an idea for what the range of relative humidity is that you might be working with. And when you're looking at an inexpensive hygrometer, you can go out there and for 40 or 50 bucks, oftentimes even less, get something with a rough accuracy of plus or minus 5% RH. Pop that into a space and see what it is that you're getting. And what you read from that, the way that you respond to that information, is fairly critical. You do have to be careful, and you have to understand what it is you're working with. But even within that plus or minus 5 to 7% range, if you put that hygrometer into a space and you begin seeing relative humidities that pop up into the 60%, the 63%, the 65% range, or at the lower end, if you start seeing things that are approaching 30% or 25%, you should understand immediately that the accuracy range on that is such that you might actually be approaching a very critical juncture in terms of preservation conditions and where you would be causing damage, even if you don't absolutely know what the specific number is. But if you start seeing RHs in the 60s or down to the low 30s, below 30%, that should really be your, shall we say, impetus to go out and get a little bit better measuring device or call someone in to work with you in terms of getting a better idea of what that RH might be. You can take the next step in terms of a handheld monitor, in terms of looking at digital data loggers. A lot of this equipment, especially for small institutions that are joining us in the US, please do consider the National Endowment for the Humanities Preservation Assistance Grants for Smaller Institutions program. Those grants are for money up to $6,000 every year. The due date is usually somewhere around the middle of May on the calendar year. But in that $6,000, if you're working with a smaller budget, especially a smaller supplies budget, they are very, very supportive of programs that come in looking for projects involving environmental monitoring, environmental data logging. So if you're looking for a way to get a couple of data loggers because you think you might have a problem somewhere within your institution, that might be a really good option for you. It's also a really nice way of getting into that NEH grant funding or that NEH program cycle. I had a colleague one time that told me that NEH PAG grants were really a gateway drug to larger grant programs, which I'm not sure is a great way of referring to it, but it does feel accurate. It's a nice introduction to it. So, and once beyond that, once you actually have some idea of what you're working with for temperature and relative humidity, please do go in and think about using different tools. The Image Permanence Institute has the online Dewpoint calculator. Most loggers that you're working with will not show Dewpoint specifically on the screen or may not even show it as part of a readout, depending on the brand that you have. But IPI's Dewpoint Calc, that www.dpcalc.org, there on the screen at the bottom. You can go in, plug in a temperature, plug in a relative humidity, and that will give you the idea of the dew point or the actual moisture content that you're working with. So there's some introductory ways that we can get a feel for what type of moisture content you might be looking at in a space. Second question that came in was really about moisture mitigation and thinking about this concept of rising damp or moisture that is coming up out of the ground. And really, this can be in two applications or two problems. It can be moisture that's coming into a foundation and rising up through the structure of a building. Rising damp can also be an impact in crawl spaces or in basements where it's coming up through a floor structure, whether that might be dirt or concrete, and actually introducing moisture into that environment, either sometimes only on the lower level, but in certain cases it may actually move through the building structure itself and move that relative humidity or move that moisture content up into the upper levels of the floor. So that first trick is really thinking about where the moisture comes from and making sure that you're approaching it from the right direction, shall we say. So it's a question of, is this a drainage issue? Is it something that your groundwater level below the building is particularly high and it will always be there? If it's a drainage issue, then we can look into mitigating it through moving moisture around the building, moving moisture past the building, improving downspouts, improving gutters off of the structure itself. But if it's actual groundwater that is coming up through, that's a very different scenario and much, much harder to control. So when we define that problem, where is it that you're actually concerned about it? Is it the moisture content, the relative humidity in a lower level or in the basement? Is it moisture getting into the upper floors? What we see in a lot of historic structures, at least in my experience, is that over time, the original floor construction, the original intent, or shall we say the structure of the floor, has been changed significantly. So as things have dried out over time, we've lost some of the seal between floorboards. You might be able to look down through and see gaps. Oftentimes there have been equipment or penetrations in the past that have come through the floor that if equipment has been removed or something has been changed, those holes have not always been filled, and it just allows for a direct air and vapor transfer between the lower level and the upper level. So if you're seeing a lot of moisture in the first floor of a building that you're concerned is coming from the basement, one way of looking at that from, if you will, a historic preservation perspective is thinking about it in terms of whether or not the floor is actually doing the job that was intended. So you can go through and you can refill some of the gaps between the floorboards. You can patch some of the holes that may be in the floor and use the floor structure itself to slow the rate of moisture transfer through the entire building. The specific question that came in, and this is a good one, we've run into this a lot of times, at least I have personally. What would you say about covering a dirt basement with plastic to reduce the rising damp that can occur between seasons? And my response to that is really, it depends. And I understand that that's a little bit of a cop-out, but it's a situation where you really do need to be careful. Recognizing first that it all depends on what your concern and what your problem is. If the primary concern is damage to the foundation, then covering the dirt floor itself in plastic isn't going to do much because the foundation is still going to be wicking moisture from the surrounding earth on the outside of the structure. So this isn't really a foundation fix. This is more, when you're looking at whether or not to seal a floor, it's more a case of the interior condition being worried about the relative humidity either in the basement space or on that upper level. Most often when I've seen plasticing the base level, or shall we say the dirt floor level, work best is if you're talking about a crawl space scenario where the space truly is not intended to be used. When we're talking about a space that only has 2 or 3 feet maybe of open space between the floor and the ground below, plastic can be an option, but recognize that once you trap that moisture underneath the plastic, it is going to sit there. It doesn't have any place to go. You're basically using a vapor barrier, an impermeable membrane, to trap that moisture into that dirt layer. And if you move that in the future, if you move it around, you have to recognize that there may actually be mold growth underneath that plastic that you're trapping into that space. The other thing to keep in mind is that if you are putting plastic down on a floor structure, on a dirt floor level, that you need to consider bringing the plastic partway up the walls, because if you only cover a portion of the space, it may slow the overall transfer, but there is still plenty of opportunity for the moisture to come around the edges of the plastic and up into the space. So do just consider carefully how it is that you're doing the application. In any case, regardless of where you're at, I would certainly recommend working with a local historic preservation resource and checking with them in terms of your building structure specifically and whether or not there has to be a concern. There may be something going on underneath that dirt layer, underneath that floor that you're not aware of, and whether there has to be a concern of trapping the moisture into that space, whether it could be damaging to a system underneath that is buried, or whether it could be damaging to the structure of the building itself. So don't just go straight in with plastic all the time, but do give it some careful thought. It can be one of the options that you can explore. And finally, this is one we're going to touch on today anyway, but I'm glad everybody wrote in about it. There were probably 2 or 3 comments that came in. What do we do about standalone dehumidifiers? The answer to that is be very, very careful. When we think about standalone dehumidifiers, and by the way, this goes for standalone air conditioners too. The units are very similar. They're just intended to do 2 different things. We use them oftentimes. I run into them most often in terms of disaster recovery, but I know that there are a lot of institutions out there, especially smaller organizations, that use them as part of regular operation. Whether you've got collections in a small room, if you're thinking about storage, if you've had one part of the building specifically that has had mold issues in the past, these things crop up all the time. They're regularly used in multiple applications, and they have their upsides and their downsides. The dehumidifiers dehumidify via subcooling. The air passes over a cold coil, the moisture condenses out, it passes over the warm coil, which is the opposite end, if you will, of the direct expansion refrigeration process. We're not going to get into that a whole ton today. But that air then is reheated by the warm side of the coil and is blown back out into the space. So if you've ever held your hand next to your portable dehumidifier, at the front of the unit or wherever the exhaust is, you're feeling warm, if you will, drier, low relative humidity air coming out. And the moisture has been condensed down into the bucket, as you can see here in the image. Right. Go. So into one of these tanks, this is where the moisture comes out. And in many cases, you actually have to go in and physically dump the moisture yourself at the end of the day or at the end of whatever cycle it is that you have programmed in. In some cases, these can be emptied out to a floor drain. That can be preferable depending on your situation. Over on the air conditioning side, these are really designed, the way they work is designed for sensible cooling, not necessarily moisture control. The process is very much the same, but instead of exhausting that warm, dry air out into the space, if you see this trunk here, this is where the warm air is being exhausted up out of a vent. It needs direct outside access or access into usually some unconditioned portion of a building, outside ideally. And through the front here is where we would feel the colder air coming out that is intended to bring the temperature down. The danger with these units is really that as we send that cold air into the space, we're not removing all of the moisture in the process. These do have tanks and they do have drains, but we're sending cold air at a higher relative humidity into the space. Even though we have removed some of the moisture and dehumidified to a certain degree, sending that cooler air in can raise the overall relative humidity in the space. And there is a danger in some cases where folks have looked for temperature control, intending to lower the temperature in a space, and have actually succeeded not only in lowering the temperature, but also raising the local relative humidity and creating a mold outbreak, not because they weren't dehumidifying, but because they were keeping the space too cold. Remember that relationship from our last discussion, that as you drop the temperature, the relative humidity goes up if the moisture content is the same. So we have to be careful with how it is that we're using these types of equipment. And specifically, this really goes for both, but I usually teach this on standalone dehumidifiers. This is something that we've known was possible for a long, long time. And I will just proceed all of this by saying this is mechanical equipment with a significant power draw that you are voluntarily introducing to a collection storage area. Now, it might seem silly to make the comparison, but none of us would ever want to put a full mechanical system exactly in the same room as all of our collections. They're dirty, they're loud, they're noisy, we have potential for leaks, we have potential for fires, we have potential for breakage, we have potential for pieces of metal flying off if a fan goes or if a bearing goes. Take your pick. A whole bunch of things can go wrong in a mechanical room, so we don't want to introduce those risks to our collection storage space. Introducing a dehumidifier, a standalone dehumidifier or a standalone air conditioner to a storage space isn't all that different. And we just have to recognize that these are issues that are on a slightly smaller scale. So in 2013, all the way up through the most recent one I'm aware of is 2016, there have been a series of equipment recalls in the United States for dehumidification units, specifically produced by the Greek corporation. I think most of the manufacturing was in China. But these brands include very common ones that we see all the time, both in residential and in commercial and cultural heritage application, base ranging from Kenmore, Frigidaire, Gree, DeLonghi, a number of others. The risk here has to be taken into account with the operation, and what follows, what's down below, are really just a number of recommendations that I would really ask anyone to consider carefully or use when you're looking at using standalone dehumidification on a regular basis. And that is only use the unit when the building is occupied. Make sure at the end of the day that the unit is unplugged, that the tanks are emptied, all the water has been drained out. Ideally, the dehumidifier should be placed on the floor. I've run into a lot of scenarios where they have them up on a stool or up on a small tabletop in order to get better circulation or just because of floor space, whatever the issue might be, maybe sometimes to keep it up out of water. If that's the case, the diagram at right is the concept of a drip loop. We want to make sure that there's no water anywhere from either the system, from the tank, from the dehumidifier that can somehow make its way via the power cable back to your electrical outlet and start an electrical fire. So please keep that in mind. Wherever possible, try not to use them for everyday use. If you do, just make sure that you're using, if you will, good practices in that process. And finally, whenever you're using these, don't be surprised if you see your electrical costs spike, especially for a smaller building. For a larger institution, for a larger structure, a library on a college campus, a larger museum, something like that, you may not notice, but especially in historic houses, the power draw for the compressors on these standalone dehumidifiers and standalone air conditioners is not insignificant, and it can make a big difference in the institution's electrical bill every month if you're using it regularly. So, moving into the meat of today's discussion, I realize that I took a fair amount of time on those, but I think they're pretty critical concepts that I hope everyone can think about as they're looking at it in their own institutions. When we think about moisture control with mechanics and with mechanical systems, we understand that this can really be applied in a lot of different structures. There are a lot of different types of buildings, there are a lot of different types of systems that we can bring into play. Most of the time, we want to do this when we're talking about a building that actually has envelope capability for mitigating, buffering, on up to hopefully controlling the movement of vapor through the envelope. So whether that's a true vapor barrier or just a series of vapor retarders, something that means that the work that we are doing to control moisture on the inside of the building, one, is not going to go and impact the envelope of the building too drastically, and two, that those differences or the difference between the vapor pressure, the moisture content that we make inside the building and what's going on outside, that all of that work doesn't just encourage more moisture to come into the building, or that we're not just pushing all the moisture that we create in terms of humidification out through the envelope of the building to the outside. We can run a humidifier all day long, and we're never going to succeed in humidifying Rochester, New York in the middle of January. So keep that in mind as you're going through, that we really want to try and use these moisture control processes in structures whose envelopes were designed to think about vapor movement, which is not usually historic buildings, to just put a not so fine point on it. And moving over a little bit here, here we go. So as I said before, just a little bit of review. Modern building envelopes, these come in all different shapes and sizes. We can look at very tight wooden structures. We can look at masonry structures, steel and concrete, glass. All of these do come into play. But the key for most of these when we're looking at a modern tight envelope is that the majority of our moisture loads are coming from one of two places, either purposefully in through the outside air that we bring into the building for human occupancy, or coming from an internal source of moisture in the building itself. So think about your bathroom at home. When someone takes a shower, you're going to have a lot of moisture introduced to that environment, which is why we see a mirror fog up or a window when we see condensation on a window. The same thing will happen in any building, generally to a lesser degree. But we are certainly generating moisture every day from bathrooms, from kitchens, from ourselves. Every time we make a cup of coffee, some of that moisture is going into the environment around you. So just recognize that we're really worried with moisture from two primary sources, what's coming in from outside and what it is that we have that we're generating on the inside of the building. Just a basic diagram here, typical components of an air handling unit for different, for a larger institution in most cases. This is a component design system. You notice here we've got return air coming back from the space. Here's where the mixed air location is. We've got outside air coming in. And let me bring the arrow up here so everybody can see this. Here's the return air coming back, and coming down the mixed air location here is the blend of the outside air with the return air. Mixed air comes in, goes through a series of filters. For dehumidification purposes, in most applications, we're going to have a cooling coil first, followed by a heating coil. We'll talk about subcool and reheat just in a minute. Most of the time after the coils within the system, we'll have a humidifier. This can actually be located in a couple of different locations or in a couple different points in the system. And you'll notice that the idea behind the humidifier is to, during certain seasons, add moisture to the airstream so that it can be blown out here to the space when we finally get to the room. And here in the room is where there's going to be a series of temperature and relative humidity sensors that are going to tell us specifically on the moisture side whether or not we need to add more moisture to the space or whether or not we need to tell the cooling coil over here to do a little bit better job dehumidifying. So just basic loop when we're talking about layout of an air handling system. We can talk more about this in the future. I'm not going to get really into the overall details of all the different system components today. We really do need to focus on the moisture perspective. So moving forward to the first one, when we think about outside air, what's going on? Well, I think it's fair enough for all of us to recognize that the goal of interior environmental control in mechanical systems is really to control what we want for temperature and relative humidity because the outdoors doesn't give it to us naturally. So when we're worried about moisture and thinking about what the impact of outside air is, we recognize that not only is this where most of the moisture that we have to contend with is coming from, either on, shall we say, the high side when it's very humid outside and we're bringing all that moisture into the building, or sometimes when it's very cold or very dry outside and we're bringing that dry air into the building and it's taking all the moisture that we want for the collection, that we want for our interior environment, and we wind up losing that because of too much dry air coming in. So not only is it the primary source of moisture, but it's also one of our key sources when it comes to particulates and gaseous pollutants that we need to filter out. But that's a discussion for another day. The outside air component here, the reason that we're so worried about this is that it is necessary for human occupancy. And it really comes down to fresh air turnover. It comes down to occupation and thinking about how many people we have in a building, which then helps the engineer calculate and estimate how much outside air we need for fresh air requirements. These are actually determined oftentimes by code and also by regular design protocols. So the intent for outside air in a building is oftentimes quite specific, and designs will call for a certain percentage of outside air to be brought in regularly. But what we recognize is that for a lot of our collections preservation environments, especially storage environments, that occupancy, the reason that we need the outside air, which is primarily human, that occupancy sometimes isn't even there. It can be extremely limited. So if we have a space with no regular occupancy, with no people, the question is, do we really need to bring a lot of outside air in? And the answer is typically no. There are a few specific situations or scenarios where we're talking about significant off-gassing or where we have collection materials. This happens more often than not, primarily in natural history collections, that are actually off-gassing or generating something that is truly harmful for human health. We talk sometimes about acetic acid and the necessity for air turnover just to get rid of the odor. So there are options or there are circumstances where we do need to bring more outside air into a space, but more often than not for your typical collection, we really don't need much in terms of outside air or fresh air, if you will. The collections don't breathe. We've talked about this in the past in the field. It was a fairly standard design consideration to think about positive pressurization in spaces in the past. And the only way that we can get positive pressurization is to bring air from someplace else, which is typically from outdoors. So we bring that extra volume of outside air in order to positively pressurize, or if you will, blow up the interior space with more air than it can hold. And as the air tries to escape somewhere, it leaks out of the room, which means that all of our conditioned air is leaking from the room rather than bringing unconditioned air into the room. This has been a past consideration, something that was regularly recommended in terms of building and especially environmental design. That is actually regularly changing. The more that we think about it today, there's a lot of movement out there, and some of the guidelines have changed or will be changing soon that are calling less for positive pressurization as the understanding going in, and really thinking about it in terms of a more neutral pressurization to the positive side, which is to say that we don't want to bring in so much outside air just to positively pressurize. But if we can make sure that we aren't bringing in air from outside the space while at the same time using a minimum of outside air, not overly pressurizing, that is the best blend of not only protecting the space, the condition in the space, but also not introducing a lot of these outside components, moisture, particulates, pollution, that we have to worry about then using energy to remove. So it's that balance. The goal at the end of the day is really thinking about making sure that you can control the quantity. We only want to bring in the bare minimum that is necessary to do the job that we need to do, whether that is the collections environment for preservation, whether that is occupancy. Carbon dioxide monitors and controls are one way of looking at this, especially from an occupancy perspective. And recognizing that control in and of itself, we talked a few minutes ago about how control really varies and that things can go wrong quickly. That image at right is the outside air damper going into a rooftop unit for a mechanical system here on the West Coast. Does that look like it's functioning properly? We can do a whole lot of work to work on control, to work on quantities. But if you go up to the roof and you realize that the damper is actually broken, and it doesn't matter what you type into the computer and what percentage of outside air you say you want, then if all the air is going to come in anyway, you're pretty well stuck in terms of how it is that you're going to try to control, or the ability to control moisture coming into that system. So just to recap that just slightly, and I want to make these just very plain points because this is something that I think oftentimes, not only in the cultural heritage side, but also in the engineering side, that we have a tendency to take things for granted. We recognize that outside air calculations are conservative. They're supposed to be. The goal really is for human health. And outside air calculations will take the largest possible, typically, the largest possible occupancy for your space and say this is the design for the amount of outside air that that system has to be able to bring in, which is fine. If you have an event in your museum or an event in your library, whatever situation you might be in, where a few times a year you might have 400 people in the room, absolutely, you need to have the capability to bring that outside air in. But for all the other days, when you only have 4 people in the room, or a very small number of people going through the gallery, or when you're closed at night and no one is in the building at all, make sure that you have the means, that you have the control designed into the system to minimize that outside air and minimize the moisture that you're bringing into the building, minimizing the work and improving the likelihood that you're going to be able to maintain the moisture conditions that you want. So close it up at night when no one's in there. And if you're worried about air getting stale, right, thinking that we don't have enough fresh air turnover, enough fresh air exchange, then set up a program, set up a design that is going to allow you to just bring it in, shall we say, on occasion. You can do this on a schedule. We've done it a number of times in the past, where instead of letting the outside air come in all the time, once every 4 hours, we'll let it open up for a half hour to a minimum content so that we get some fresh air turnover in the space. And if you're worried about that little bit of acetic acid smell or a little bit of the old book smell, then that gets some air exchange in there. It brings some fresh air in at a minimum quantity, and we get a little bit of air turnover instead of just working through recirculation mode all the time. But again, minimize it. Think about how it is that you can control the actual amounts that you're bringing in the effort to not bring all that moisture into the system all the time, into the building all the time. And finally, using CO2 sensors, and if there is no call for outside air, don't feel like you need to open it up. The collection specifically typically does not require it. And like I said, there are very few exceptions that we need to think about, but those are really case-by-case points. Managing dew point, we really have typically 3 options that we want to approach. The first one is just recognizing that whatever is going on outside, we can just let it happen inside. And we talked about this with historic structures, that if we have no means of moisture control, then that's what's going to happen. It's going to do whatever's going on outside. Mechanically, we have the option of adding moisture, so we can humidify. And we also have the option mechanically to remove moisture or dehumidify. So let's take a look here for a second and think about what each of those look like. Now imagine, if you will, please don't take away from this that I am encouraging anyone to use a 70-50 set point. This is kind of the old standard going back into my formative years, if you will. But thinking about that condition that we've all used for so many years, that we're working on changing, that we understand the science has really changed. At 70 degrees, 50% relative humidity means that we need a 50-degree dew point. And if I'm sitting in New York, right, this is what last year's outdoor dew point chart looked like. Now, if I want to maintain, let me get the arrow turned on here. There we go. If I want to maintain a 50-degree dew point inside my building, which is this line going across the screen, everything down here, all the days of the year where I'm at these dew point conditions lower than 50 degrees, that means that I have to be humidifying in order to bring it up to a 50-degree dew point to maintain that flat line control. And all of these days, all these hours of the year up here, where we're above a 50-degree dew point, I have to dehumidify in order to bring that moisture content down to my right interior content to maintain that flat line. So the takeaway here is that if we want to look at that flat line control indoors, that 70-degree, 50% relative humidity condition, I have to work on moisture content all year long. If I look at the number of days, the number of hours in the year that outdoors in New York City gives me the actual moisture content that I'm looking for, it might be limited to, if we add up hours, maybe the total of 3 or 4 days, tops. Most of the time, outdoor moisture contents simply do not match what we're looking for inside, especially if we're thinking about very fine-tuned flat-line moisture control conditions. Now, let's change a slightly different model to that. What do we do? If we start thinking about our different, or shall we say, new conditions for preservation environments and thinking about where risk actually occurs, we discussed this ever so briefly last month. But thinking about that upper limit of 55% relative humidity and that lower limit of 35% relative humidity with a little bit of a seasonal temperature change in there. And these are really seasonal set points that we're thinking about as a control scenario. What is it that we can do that maybe has a little bit of impact on energy, Certainly in the wintertime, some benefit for preservation, not a whole lot of impact in the summertime in terms of what we're doing to the overall rate of chemical decay. This is fairly safe. This is what we've talked about the last 5 or 6, actually going on probably 10 years now in the field. If we plug these into that same chart, what is the work, what does the aspect of moisture control start to look like? And here we are. That now notice that 70-55 condition was a 53-degree dew point, and that 65 degrees and 35% relative humidity was here at about a 36 or 37-degree dew point. So when we look at this range, we know that in the summertime, anything that is above that 53-degree dew point, and for all of you that are joining us from overseas, I do apologize that I'm only talking in Fahrenheit today. That is a note, I think, for next time that I'll try to keep in mind, is to certainly do both. But for everything that is over 53 degrees Fahrenheit, we do still have to dehumidify. And that has reduced, if you will, the overall amount of moisture control that we need to do. In other words, there are a few more days right here underneath the line between 50 and 53 where we've said that the outdoor moisture content is okay. But especially notice here on the lower end that if we start to think about the ability in the wintertime to use a seasonal set point of 65 degrees and 35% relative humidity, notice that when we get to that 36 or 37-degree dew point, that this is my control point. This is all the higher I need to bring the moisture content when I'm humidifying. So it's all this time underneath. But what I'm left with in between that 36-degree dew point and that 53-degree dew point are a whole bunch of days within the year that the outdoor moisture content, primarily in the swing seasons, at least here in the US, in New York, here's the fall and here's the spring, are a whole bunch of days where the outdoor moisture content is actually not so bad compared to what I'm trying to do inside. We recognize that if my moisture content is in between these two values, that I'm somewhere within the range of that 65-35 up to 70-55 condition that I'm happy with. So this essentially means from a moisture control perspective that we don't have to do any work. We don't have to expend energy in order to control this moisture content. And what that adds up to, this is the point I think really to take home. That when we're thinking about the amount of work that we have to do, in other words, how much time we have to spend controlling moisture in these scenarios, for that first scenario where we're trying to work with a flatline 50-degree dew point, we have to dehumidify in New York City 41% of the year. We have to humidify 59% of the year. And I realize that that adds up to a perfect 100%. There are a few days in there where it gives us outdoors an exact 50-degree Fahrenheit, but as I said, it's not very often. We're working on all of that air all of the time to control the moisture content. But that scenario B, where we start thinking about seasonal set points and the ability to use a lower moisture content in the wintertime, and allowing the moisture content sometimes, depending on the situation or the environment, to creep up slightly in the summertime, up to about 55% relative humidity, means that now, instead of 41% of the year, we've reduced the amount of dehumidification we have to do. We're only now looking at 37% of the year to dehumidify, at least based on outside air qualities. And for humidification, when we're looking at outside air moisture content, now we only have to humidify 35% of the year instead of almost 60%. Which means that when we're thinking about when it is that the outdoors matches our indoor moisture content range, nearly 30% of the year, at least in New York in 2017, we could have had moisture conditions that were allowable, that we wouldn't have to think about, shall we say, extensive moisture control. We could really just think about sensible temperature control. And this is a very critical factor when it comes down not only to energy management and energy considerations for moisture control, but also the ability and thinking about the realistic ability to control environments within a particular space. For anybody out there who has tried to run flatline control, we all know how challenging that can be, and the question of whether or not that actually works. Most of the time we get a lot of complaints that I can't maintain my flatline condition. I think if we recognize where the risks for collections are and what is the safe range for collections environments, and the fact that that is certainly broader than we have thought or discussed in the past, that we really have some opportunities for better control in terms of the amount of success that we can achieve, and also reducing the overall energy portion or energy content that we're using to do that work. So common mechanical dehumidification processes or equipment, if you will. The first one that we'll talk about is dehumidification via subcooling and reheating. And this is a process that is very common to a lot of institutions out there. It can happen in a lot of different system designs. It can happen in all kinds of scenarios where some institutions will have chilled water and hot water in terms of cooling and reheat coils. Some institutions, instead of using chilled water, will just be using a straight up direct expansion or refrigerant based system as their cooling capability. But the key here is that we are actually working through the, if you will, the psychrometric process to understand that we can remove moisture from the air and then change the quality or change the temperature condition of that air before we send it back out to the space. The general rundown, we'll go through this in the system in just a moment, is that as the air enters the cooling coil, we know that it's at a warmer temperature from the space, and this is usually the blended condition of the return air and the outside air. It comes in at a warm temperature and a higher dew point than what it is that we want. As we cross that cooling coil, the cooling coil's job is then to subcool the temperature of the air down below the dew point condition. And if you remember from the diagram from last month, when we drop the temperature below the dew point, we allow moisture to condense off. That's one of our primary means of dehumidifying. So as we subcool below the dew point temperature of the incoming air, that condensation then drops out, and we can drain that water off and we achieve the lower dew point, leaving the cooling coil. As that air leaves the cooling coil, that dew point will be lower. The sensible temperature will generally be quite almost equal to the dew point condition, which means that that leaving air condition from a relative humidity perspective will be nearly at 100%, if not exactly. The problem is that we can't send that super cooled 100% relative humidity air straight out to the space. If we did, if we were sending out 45-degree air into a space at 100% relative humidity, if we didn't have enough heat energy in the space to raise the temperature of the air, we could wind up very easily with a condition somewhere in the range of 55 degrees and almost 80% relative humidity coming out of the diffuser out of a supply air duct into the space, which is going to cause a lot of problems in a real big hurry. So we know that we can't just send that subcooled air directly into the space. We do actually have to reheat that condition. So we're going to take that saturated air, we're here at this point, we're going to take that saturated air from the cooling coil at that low temperature, that same equal dew point and a high relative humidity. And if you remember those relationships that we talked about last month, we're going to raise the temperature of the air in order to bring the relative humidity down. But the dew point does not change. And finally, we take that warmer air at that lower relative humidity condition, and we send it downstream to the collection space. And what I'm actually going to do here is just walk through that. Bear with me for one moment. On this diagram here, we were talking about where the air comes in, the mixed air condition with a high temperature, warm temperature, high dew point condition. We take it across the cooling coil here. That drops the moisture out as we subcool. In this space between the cooling coil and the heating coil, between here and here, we're going to make sure this is where the air comes off the cooling coil at a very cool temperature, a very high relative humidity, oftentimes 100% RH. We then reheat that air, we bring the temperature up, we bring the relative humidity down, and that creates the safe condition to then supply out to the space. And the heat load in the space is what does the rest of the reheat for us. On a hot day, depending on where we're at, we may send 60-degree air into a space that we want to wind up at 70 degrees. That extra 10-degree condition comes from the room itself. It comes from the heat load on the room. So we send 60-degree out at a relative humidity maybe around 60 to 63%. And by the time we get here and it raises the temperature by 10 degrees, we've dropped the relative humidity down to around 50%. So what that looks like, that's what it would look like in terms of the system layout. I'll drop that arrow for us. One second. And the equipment that does it, this cooling coil here, it's pretty straightforward. We can talk about this more in kind of a broader HVAC discussion, but that cooling coil is really just a construction of copper tubing, usually with aluminum fin tube attached to the copper. It creates a greater surface area for the air to come in contact with, and we circulate some sort of cold media, whether chilled water, whether refrigerant, through that in order to drop the temperature of the air and condense the moisture off. When that happens, the air comes through the coil, comes in contact with the coils here. The temperature of the air cools, the moisture condenses out, and we see the moisture begin to collect here in these drip pans. Here's one on the upper level of the drain. dropping down to the drip pan or the condensate pan here on the lower level that would have the floor drain. And that's how we evacuate the water from the system. Now, beyond cooling coil, beyond subcool and reheat, and using a cooling coil as our means of dehumidification, the other most common practice in terms of straight up dehumidifying for cultural heritage institutions has really become active desiccant dehumidification. And this is something that if we have some conservators or we have some exhibit folks in the audience, I think the concepts here are going to sound relatively familiar, because if you hear that term desiccant and you go, oh, silica, I know what you're talking about, you're absolutely on the right track. It's just silica in a different configuration, if you will. So when we think about desiccant dehumidification, we're using a desiccant media, which is typically silica, that's embedded on a wheel, and it absorbs moisture from the airstream that we need to dehumidify. And that wheel with the embedded silica rotates through the airstream. So at any given point, part of that wheel is taking on air, taking on moisture from the airstream, and as it rotates back out, it's then going to use a separate airflow to drive the moisture off of the wheel. And if you will, recharge the silica the same way that we would in a passive situation, where we are allowing silica to absorb moisture in a case for a few weeks or a month or so, and then we come bring it out and we have to recharge the silica or regenerate it. So in that process, we have the heated reactivation air that blows on that moisture-laden section. It evaporates the moisture off and exhausts it to the outside, and it leaves that section of the wheel very warm. That heated section of the wheel then rotates back into the air that we need to dehumidify, and allows, remember when we talked about our buckets during the last conversation, that when we talk about heated surfaces or heated air volumes, we can take on greater amounts of moisture. Well, that heated silica is what allows us to then absorb a greater amount of moisture from the airstream. So as that heated section turns back into the airstream that we need to dehumidify, it absorbs the moisture from the airstream, dehumidifies it, and rotates that moisture back out to be evacuated at this stage. Finally, the air that leaves the wheel after passing through that heated section is going to exhaust off of the wheel into a hot temperature but a very low dew point condition. And that's what then is going to be used to supply downstream after we've used a cooling coil to bring the temperature back down. So when we look at that in a layout configuration, we get a scenario that looks something like this. This is just one example. There are a few different ways that this can be covered. We have return air coming back and outside air coming into the mixed air location here. Now, in this particular case, we have a wheel that is only filling up half of the airstream. So here's the part of the wheel that is going to absorb the moisture. And as the air comes through, the moisture is entrained in the wheel here into the silica. The wheel then rotates down into this secondary airstream. And as we talked about, what happens here is that the air comes in, is superheated, and is sent through the wheel here to heat this portion of the wheel and evaporate the moisture off of the wheel that has come from this location. It evaporates that moisture and exhausts that hot, humid air back out of the building. While up here, the moisture that has been absorbed on the wheel here, the air that passes through, is now going to be at a warm condition, but a relatively dry condition. It will be hot and dry, if you will. So that hot, dry air has to be cooled in order to get it to the right condition to send now downstream out to the space. So this is a technology when we look at desiccants, desiccant technologies, these are operations and systems that work in conjunction with another form of cooling. Whether that's going to be chilled water, whether that's going to be refrigerant-based cooling. Now, as we move into humidification and the concept of adding moisture to the air, this shows up in a lot of different applications or a lot of different settings. I think a lot of us are more used to it in the idea of cold regions or seasonally cold regions where we have low moisture contents outdoors, and we really need to bring up the interior moisture content for a lot of collection materials. But there are a lot of places throughout the world, if you live in a dry region, if you live in an arid region, where you may actually want some degree of humidification all the time, depending on what your collection might be or what the collection requirement is. And one caution in here is that this goes back to past standards and past ways of thinking about what minimum relative humidity should look like, which is just to say that it's obviously not a one-size-fits-all scenario. And when you're thinking about whether or not you actually need humidification in your institution, in your storage environment for the collection, think about what the collection has been exposed to in the past. I've walked into a lot of situations in the Southwest United States where the design intent was to raise the relative humidity to 45%, even though the collection originated from that region and was really not used to relative humidity conditions much over 30 to 35%. So we were really trying mechanically to do something that had been, shall we say, broadly defined by preservation standards without looking specifically at what those objects were used to, what the environment was that they were created within, what the appropriate moisture condition for that specific collection would be for the long term. In other words, there's some places where we can over-apply humidification fairly easily on the collection side, but also, as we talked about last week, on the historic envelope or historic house side. There are a couple different ways that we can humidify. We've got isothermal technologies that are steam-based, and we've got adiabatic systems that are going to be evaporative. The idea behind all of them is that they're a means of adding moisture into the airstream. And the trick is that we have to control how much moisture we're adding into the airstream so that we don't go beyond the relative humidity condition that we're looking for. And one of the things that really does come up is we will see a lot of systems from this gets into older systems and, shall we say, non-specific cultural heritage applications. We get into a lot of scenarios where systems will be capable of a little bit of dehumidification. It's not really what they're designed to do, but they're doing enough. It's like taking your window air conditioner and recognizing that you do dehumidify with it, even though that's not really what it's meant for. So that can happen even by accident. But when we're thinking about humidification, it doesn't happen unless the equipment is there in the system. There's no other means of doing this, half-heartedly or to a very little degree. You have to have the humidifier there in the system design. And for spaces that were originally designed looking at human comfort and looking, if you will, at human comfort environment conditions, that 70 degrees condition that we're not really thinking about moisture control, if the humidifier isn't there, then you're not going to be able to control relative humidity either in the wintertime or in a dry environment. This happens in a lot of older buildings, a lot of repurposed buildings, where you walk in and if you're using environmental data logging, you discover pretty quickly that in the wintertime, you may be able to manage your temperature okay. You may be somewhere between 65 or 70 degrees, somewhere in that range. But all of a sudden, you notice that your interior relative humidities are dropping down into the 15%, the 10%. I was in a place a few months ago that was down to 3% relative humidity, and at that point, I wasn't even sure if the logger was working properly. But we can get really dry, especially in very cold environments. And if the humidification isn't there, if it hasn't been designed into the system, there's not much that we can do in terms of overcoming that. So this is something to really consider, first of all, whether or not you have the capability, whether or not the collection requires the capability. Think about that. But also consider whether or not your building was designed for humidification. There are many, many, many things that can go wrong in this process on the envelope side, on the collection side, on the control side. Humidification is not the easiest mechanical process, but it is critical for some collections environments. So as we look at that and think about it, talking about equipment options, and I'm just now realizing that that text is quite small. I apologize for that. Isothermal systems, when we think about steam comes from a couple of different places, and we have a few different means or ways of creating it. We can have direct steam that is coming from a steam source either in the building, typically a boiler, or from, if you're on a campus or if you're on a larger institution, you may have a central steam plant that feeds steam over and allows steam to be piped into a humidifier wand. The one thing to keep in mind about direct steam, and it's not just for direct steam, but this is usually where it crops up, is that if you're using direct steam that is also used for heating in other parts of the building, in other words, humidification is not the primary reason that you're generating that steam. A lot of boilers, a lot of larger steam boilers, have to have certain chemicals added to them in order to keep the interior of the boiler from scaling up. And these are various types of acids that get added to the water stream itself. The problem when you use that direct steam to then humidify with is that you're actually humidifying, or if you will, pushing that steam into the space that is containing the acid that has been added to the system in order to keep the boiler clean. That's great for the boiler. It's kind of lousy for your artwork. So keep that in mind, that if you're looking at humidification and someone suggests a direct steam system for you that is piped directly off of the steam heat that you're using elsewhere in the building, you may want to interject and say, wait a minute, I want a different source of water. And this is where we get into steam-to-steam humidification. This is where we oftentimes will use building steam through a heat exchanger to create steam for us from a different water source. And that water source can be anything from RO water, reverse osmosis, to, oh, take your pick, DI water, oftentimes even just sometimes filtered building water, which still isn't great. Especially you want to be very careful about softened water that adds salts to the process. But for even just building water, as long as you're okay with the mineral content, that's still better oftentimes than the acid content in building steam. So you can use steam to steam heat exchangers to create a cleaner or clean steam, if you will. And then the third option oftentimes for this isothermal technology is that we can use what are called electric canister systems that are basically essentially miniature-sized hot water tanks. So if you have a hot water tank in your home and you know that the element goes in through the top of the tank, is electrically charged, that causes the water inside the tank to boil, and that's what heats the water. Same basic system. There's a small tank within this particular unit. The electrical charge then boils the water, and the steam that comes off is what is used to humidify with. Now, the upside there is that these are very small, very compact systems, which is why they get installed quite a bit. From a maintenance perspective, they're a little bit tricky. We'll talk about that here in just a minute. But these are a very common application that you will probably see at least once in your career if you're looking at humidification systems. The adiabatic systems, the evaporative systems, are a little bit less typically common, but they do get used again, as I said, in that hot, arid environment. The US Southwest is where we do see a lot more of these. But the idea behind it is that you don't actually have to generate steam, which has that heat component, in order to achieve the humidification. So you can do humidification via ultrasonic. In other words, you can encourage agitation, or you can look at ways of improving evaporation of moisture into the air. This can be a pressurized cool mist or a cool fog system where you take basically a pipe with pinholes in it, and you pressurize water through the pipe and just allow it to spritz or spray out into the airstream, and it then evaporates and becomes entrained into the airstream down through the unit. And third form is an evaporative pad. These have varying degrees of success and cultural heritage. The one thing that I will caution you with evaporative pads, depending, there are ways to avoid it, but you have to be very careful with bacterial or biological growth, especially mold growth, when we're thinking about evaporative pad systems and a media that is constantly soaked in order to provide that evaporative humidification you're looking for. And we'll talk about that here in just a second as a specific system. So issues to consider. If you're working in a cold environment or in an older envelope that maybe doesn't have modern windows or a modern vapor barrier, condensation is common, right? I think we've probably all seen it at one point or another, even just in the setting of our own homes, where we are looking at condensation on windows, other cold surfaces, sometimes exterior walls. This is not unusual. It happens regularly. In some buildings, you will see what we call perimeter heat systems that sit underneath windows to throw a warm wash of air up over the window surface to try and increase the temperature to reduce the likelihood of condensation. It's not uncommon at all, especially you do see it an awful lot in the northern US. Issues when we talked about last time in historic envelopes, thinking about issues of spalling, cracking, and efflorescence. Humidification is, if you have humidification in an historic building, oftentimes it's not a matter of if you will run into these problems, but simply a question of when. And you have to monitor your environment carefully to find out whether or not you're running into that issue and monitor the building structure as well. Controlling capacity issues, whether or not you can actually get it to the relative humidity that you were looking for, and whether or not wouldn't you know, so I mentioned I was coming from Seattle today. I didn't mention I was in a hotel room, so I never get phone calls in a hotel, but I guess there's a first time for everything. Apologize for that. That was interesting. Anyway, going back to capacity, making sure that you have the design capacity for the humidifier that you need. In other words, if you're looking for a certain level of relative humidity in the wintertime, the humidifier has to be sized appropriately. And if the water capacity, if the humidification capacity isn't there, you're not going to hit your set point. Very nice, Tara. She just wrote in whether or not that was my wake-up call. Thanks a lot. At least it got me out of the chair. What is your water source? We talked about that just a second ago. And when you question whether or not you're using building water, if you're using treated steam, or whether or not you can have some sort of a clean water source like an RO system. Finally, on the maintenance side, humidifiers for our facilities friends are one of the banes of their existence when it comes to maintenance. For whatever reason, these things never seem to work properly. Typically, they need preventive maintenance at least twice a year before you want to get them started up, well before you actually need it to work. And typically at the end of the year too, to make sure that everything has worked properly, that valves are appropriately closed for the season. One of the worst surprises that any cultural institution can have is realizing that you've moved into the summer months and summer operation and your humidifier is still leaking moisture into the airstream. It makes it awfully hard on your dehumidification system to try and maintain those right conditions. So moving through year-round humidification for areas that, again, have a year-round dry condition or a year-round arid environment, direct steam isn't always that option. You really don't want that added heat, so you're going with those adiabatic systems. Move forward here a little bit. Evaporative cooling, now I bring this up because it isn't actually designed for moisture control, but it kind of does it as a side effect, if you will. For folks that are familiar with evaporative cooling, great. If you're not familiar with evaporative cooling, it's probably because you don't need it. Evaporative cooling is also referred to kind of colloquially as swamp coolers. And the idea is that you're using the heat of vaporization to, or the heat of evaporation to cool the air via entraining moisture into it. So you're bringing dry, hot air into this unit, and I'll use the arrow point out here, where we have the dry outdoor air that is coming in, and it passes over. Remember what we were talking about, that soaked pad that is humidification in some systems? In this case, that soaked pad is actually performing the cooling for us. So that hot, dry outdoor air comes in, hits this saturated pad that is full of water, which then cools the air. As the air takes on moisture, the temperature will drop. It loses some of its heat energy. And the temperature of the air drops, and that cool, moist air is then pushed out to the building and distributed throughout the structure. Now, we don't see swamp coolers very often except in these very dry regions. And from a collections perspective, they're not my favorite equipment, primarily because that moisture perspective is very, very hard to control. And the amount of cooling that you actually get varies significantly by the outdoor temperature of the air. So if it's not a particularly hot day, you may not actually cool effectively because you can't evaporate enough moisture into the air. So these are systems that are really meant to create human comfort environments that can vary greatly across the board. When we try to put those into cultural heritage applications, my experience is that they don't work overly well. And most of the time we're better off using a different type of technology. But I threw it in here because some of you may be looking at these types of systems in your institutions and may be wondering, gosh, why can't I ever maintain a constant temperature? Why is it that my relative humidity is bouncing up and down all over the place? It's because you may be getting some humidification as a result of this sensible cooling process, but it's not really intended to control or to add moisture to the air in any sort of controllable quantity. And anything on here that I didn't just cover? The main thing is really just that there is no capability for dehumidification in this system. And it is something that I will point out. There are environments globally that are truly arid year-round, but we want to be careful in the application of this type of system because many environments will still have what we would refer to as a rainy season or a wet season. And even if that is only a few weeks to a month, month and a half, for that few weeks up to a couple of months, this evaporative cooling system is not going to work properly. It's not going to be able to cool, and you're going to be dealing with situations where you have high outdoor moisture contents, and you have a system that is automatically, by its design, adding additional moisture to that airstream if you're bringing outside air in. So do consider what your yearly environment looks like, what your outdoor environment looks like over the course of a year, and whether or not this is going to be the appropriate application, or whether you really do need a system that is capable of both mechanical dehumidification as well as mechanical humidification. All right, got about 15 minutes left. So I am going to say at this stage that I'm just going to chat here for a few minutes about systems and disaster response, because I think, as I said at the outset, that this is kind of a developing field, that I think there's more thinking to do. I'm going to run through the basic responses real quick, and then just kind of talk through the ways that I think we might want to consider learning, experimenting, thinking, communicating more about how to change those. I feel like my knowledge, my typical response, what it is that I've been taught over the last 18 months in particular, has not been challenged, but that I'm really being encouraged to rethink that in terms of what it is that we have to do moving forward. That we thought we had one thing, and now that certain events have transpired, especially looking at what Florida and Puerto Rico went through, and really, I think if we'd been paying attention a little bit more, what we would have learned from Katrina, I don't know that we were quite there as a field. But I think Katrina also is a good example of this in terms of what we need to think about for mechanical systems and disaster response. The reality is that the issues can vary. We think about disasters in terms of being natural events, right? Hurricanes, tornadoes, blizzards, take your pick. What is it that might go wrong? But I think more and more as we get into the modern world as we know it, there have been a number of instances of long-term brownouts that have happened throughout various geographic regions for long periods of time, whether we look at that as a matter of a day, to things that are driven by natural disasters, that are driven by storms or something else. In the case of sections of Puerto Rico only recovering power just a few weeks ago, nearly a year later after the storms. So the issues and what it is that can cause the problem really do vary over time. And in the past, our way of thinking about this from an engineering perspective for cultural heritage has really been one of redundancy. And it's saying, and the redundancy perspective was looking at it and saying, well, if one piece of the system fails, if it breaks, then I want to have another piece of the system there to do it. Or if my main system is too big to run on the generator, then I'm going to have a smaller portion of that system that is capable of being run with the generator if for some reason we have a natural disaster event or a storm event. And so that idea of redundancy meant that systems were designed with multiple components. And in a lot of cases, that meant two chillers. In other words, what was generating your chilled water for cooling and dehumidification. Sometimes it was multiple coils lined up one after another. One coil was attached to one chiller, another coil was attached to a different chiller. And the idea again was if we lose either power or if we lose a single piece of equipment, we have a backup there that's available. But imagine from a first cost the limitations here that you're basically installing two of an awful lot of the pieces of your system from the very outset. You're not always doubling the cost of installation, but you're adding a pretty significant percentage to look at having redundant equipment throughout your design. Now, this is still used, and I don't want to poo-poo redundancy because it does certainly have a role to play when we think about it today. But that redundancy has changed quite a bit, and we really look at it in terms of what are the most critical components. And where is it that we can do it without a lot of impact on cost? Fan wall technologies, where instead of using a single very large fan, now we're using what's called a fan wall configuration, where we have maybe 4, 6, sometimes 8 or 12 fans that are controlled in unison with one another. So if we lose a single motor or if we don't have the energy to run all 12, we have the option of running the ones that aren't broken, or at least of running only a portion of them depending on the energy that we might have available. So we can do that with fan walls. And humidifiers are another one where it comes up. This is primarily a maintenance thing, especially for organizations that are in farther north regions. When we lose humidification in the wintertime, that can be really bad news really quickly for some different collection types. And there's a lot of encouragement in terms of installing dual humidifiers, which are a relatively low cost portion of the system, so that if we have a maintenance problem with one, we have a backup that is ready to go online and continue that humidification work in critical collection zones. So that's something to consider. But really, instead of redundancy, what we're talking about more now through the design community, and I mean, resiliency is a concept both in mechanical and engineering design, but also in terms of architectural design. They're talking about resiliency in buildings. And I think for our purposes in cultural heritage, that we really want to take both of those discussions and sort of bring them into our discussion of this concept of resiliency and how it is that structures, systems, spaces can flex with what it is that is happening in the exterior environment. And this resiliency has an awful lot to do with envelopes. It has a lot to do with ways that you run a system, shall we say, various levels of running a system. But it also has to do with really learning about what the behavior of your space is typically going to be. And we did a lot of this a few years ago with some of the shutdown experimentation, the optimization experimentation, and thinking about what is it that we can, how long will a space coast, if you will? How long will a collection space, if we take the air away, if we take the mechanical system away, how long will it maintain its conditions just as a normal course of being, treating the collection space like the refrigerator? If the power goes out and you don't open the refrigerator, it'll be good for a while. But the instant you open the refrigerator, you know that you've lost that cool air and you've introduced the warm air into that environment. Resiliency has a lot to do with that. How long can our building coast or take care of itself until the outdoors is finally going to overcome what the building structure is capable of buffering? And this is different for every structure. It's different for every building. It's something that we learned very poignantly, I think, in Puerto Rico. That and it's a very interesting spectrum that the historic structures in Puerto Rico, at least in my experiences, the institutions that I worked with and that I visited, the historic structures lost their environmental control, what they had, much more quickly. But over the long term of the power outage, generally performed much better because they had the capability to allow for natural ventilation and allow for natural airflow, which oftentimes, to a certain degree, mitigated or lessened the degree of the mold outbreak, at least in a collections environment. Whereas when we were looking at modern spaces, when we're looking at modern environments that were very tightly constructed, very sealed in terms of air and vapor, initially when we lost power, initially when we had problems, as long as the space didn't have water incursion, it made it okay for a little while. But I think what we found is that for those long-term power outages, now all of a sudden there was a very fine line between how long that space could manage on its own and when we needed that natural ventilation, when we needed to have that airflow. And in many circumstances, we're unable to achieve it because of how tightly the space was constructed. And this is a really critical factor in terms of thinking about resiliency. That resiliency, on one hand, is that we do want the space to buffer for as long as possible. But we also have to recognize that when the space can no longer buffer, when the outdoors is simply overcoming what the building can limit, then we need to be able to move to a different means of operation, to a different means of control, and be able to think about natural ventilation, which is typically not a design concept or not a design criteria when we're thinking about tightly controlled environmental collections environments. And finally, it's funny, everybody's response when we lose power in a setting, and this is everywhere these days, generators are far more common than they were even 15 or 20 years ago. Folks are going, well, just get a generator, make sure you have fuel. But what if you don't have fuel? What if you can't get fuel? And what if you don't have a generator? What is it then we need to think about from that mechanical system perspective? I'll go here, and again, I'm just going to say real quick that I'm happy to go a few minutes over on this. It's 12:23. We've got about 7 minutes left, so please do send those questions in, and I'll take as many as we can within the time that we have. But I'm happy to stay after a little bit longer for folks who want to stick around. So when we're thinking about mechanical systems and disaster response, we want to think about what it is that we need to know beforehand. And I think this is something that I've been thinking about more, that I certainly haven't, formulated for myself. And I'm not sure if a formulation of it really exists out there, at least not that I've seen entirely. But things that we need to think about for disaster preparedness beforehand is really understand we have a means of testing a power outage to a degree, right? And that's thinking about shutdowns and setbacks. So if you have an environment that the envelope has been designed to help buffer the outdoor conditions, test a shutdown. See what happens when you lose power in that space. Make sure the lights are off, obviously. But if you lose power in a space, how long, via using data loggers, how long do your interior conditions look okay? After a day, if everything looks pretty good, then maybe you're starting to get an idea of how long it is that you can go without power before you really have to be concerned or before you have to worry, and know that it's time to start circulating and ventilating that space, or at least finding ways to circulate and ventilate if they're not built into the system design. So think about that as a means of testing, how long it is that your space can actually hold out before it's time to start introducing outside air or natural ventilation. For at-risk areas, and I realize that everybody is at risk in some regard. We had Sandy in New York City a few years back, and we've had a slew of really unfortunate hurricane seasons in the southeast U.S. Um, for these at-risk areas, I want to give some more thought to this, and I think that we need to do so as a field. I think we need to reconsider our design for collections environments in a lot of these institutions and a lot of these regions. And it's not to say that we can't do tight envelope control and tight envelope construction in a hot and humid environment. We still can. We have the capacity to build to that. But I think when we design that, we have to understand that there needs to be a means of providing natural ventilation when necessary. When these events occur, that we can't just rely on the fact that the refrigerator is going to stay closed. Eventually, the outside condition is going to get in, and we need to make sure that we have a way of circulating air through that environment in order to restrict or reduce mold growth or the risk of mold growth, and in order to make sure that we can at least minimize the overall environmental damage that occurs. And that's not an easy situation, or not a real easy discussion, because it really does change a lot of what we've had on the table in terms of design discussions for the last few decades. But I think we're at the point now where we really need to think about this carefully. For a lot of institutions, low-tech solutions may be the answer. This is a question that folks often bring up: is my generator large enough to run my mechanical system? It might be large enough to run a portion of it or one of your mechanical systems, but typically not your entire building or all of your environmental or collection storage. So think about what your low-tech solutions might be, and think about something as simple as circulation fans. That if you don't have the ability, if you don't have the generator capacity in your institution, if there's a power outage, to bring your full HVAC back up online, at least bring circulation back up online, at least be able to move air through the building. Even if you're not looking at running, cooling, not looking at dehumidifying, anything like that, think about air circulation first. So really thinking about what our immediate response is going to be in terms of HVAC, and identifying what those critical operations and spaces are. Because it's very tempting to say, well, we want to take care of everything. We need to take care of the galleries. We need to take care of the storage spaces. We need to take care of the offices, whatever. I know most of us will generally drop the offices off the list of critical spaces, but it is also thinking very carefully about what are the truly critical environments that you need to bring online first, if that's going to be a possibility. And also thinking about where in this process do you start relocating materials to your critical zone that you're going to be able to maintain a condition if you can maintain control. And finally, the other part that comes into this, and this is something that I know folks that have been on the ground in disasters sometimes take this for granted from a human safety perspective, in terms of not being allowed to go back into a building until it's been declared safe. But for especially mechanical systems and collections environments, if the interior of the equipment has been wet or exposed to weather, and I'm not talking about rooftop units that are designed to be out in the weather all the time, but if a panel has come off of that unit and the water has gotten in, or if your mechanical equipment is in a basement that flooded, do not start that equipment back up until you've had it checked by a professional to make sure that the electrical connections, to make sure the coils aren't blocked, to make sure that the fan is not impeded, so that it can run safely and be able to achieve what you're looking for. You start that up without having it checked, going back in. You're asking not only for trouble with the system itself, but there's every possibility that those problems could then travel downstream and create a bigger problem than what you have to begin with. Let's see here. So, final thoughts. I tell you what, I'm just going to kind of lead these here. And Jess, do you want to jump in and kind of get me going on a couple of questions here for 10-15 minutes or so?
Sure. Well, first of all, thank you so much for that great content. And I recognize that some of the participants might have only budgeted the 90 minutes for this program, so I'm just going to go ahead and hopefully this won't block this final slide here. But if you all do need to leave, we would still appreciate your feedback. So if you can just click on the survey link and load that to finish for later. That would be great. So we had a few questions come in, and we'll start off with one from Tara Kennedy, who was wondering if building occupancy matters in terms of the moisture load. So do more people affect the moisture load or just the thermal load?
Sure. No, it's a really good question, Tara, and the answer is absolutely yes. All of us exhaust moisture every time we breathe. So the more people we get into a space, it certainly does impact the moisture load, which is why when we're thinking about those spaces where high occupancy is a possibility, galleries or public spaces that might be used for events, then we need to think about the amount of dehumidification capacity that the system is capable of. For a lot of storage environments, it's a less critical issue because there are very, very rare occasions where the occupancy in a storage environment would be greater than what the dehumidification design is capable of. So when we think about the moisture impact of people and dehumidification specifically, it's really in a gallery scenario or in that public space and making sure that we have that design built in.
Okay, so we actually had a handful of questions from Tara. And she also asked, why is or was positive pressurization necessary for building design? Is it certain buildings? Does it pertain to modern building design? Or is it a past practice for older buildings?
It's a little bit of all of the above. The idea behind positive pressurization is that if we're pushing air out of the space that we are trying to condition, it means that the bad air, if you will, on the outside, the air that has not been cooled, that has not been dehumidified or humidified or heated, it means that air from the exterior environment cannot get into our conditioned space. And that's the idea. We talked about this with diffusion last time and how vapor pressure and air pressure are two different things. But pressurization, when we're talking about air pressure, is all about forcing air out of our environment so that you can't let unconditioned air into the controlled space. And the problem with that is really there are a few problems with it. From an historic envelope perspective, that can cause a lot of problems. Positive pressurization in historic buildings is a root cause, and not the only root cause, but a root cause of a lot of the envelope issues that we have in historic structures. Because as we pressurize the interior of that historic space, we are forcing those temperatures, whether warmer or cooler, as well as that vapor, whether it's drier or wetter, depending on the season and depending on the operation, we are forcing that harder out through the envelope. And it means that the envelope is taking on that temperature differential. It means it's taking on that vapor differential that it oftentimes wasn't designed for. So pressurization in historic buildings is a very, very significant issue. And I should say not just historic, but in any building whose envelope was not designed for it. I see this even in a lot of buildings that date from the 1970s in particular, where we didn't understand much about envelope design. We didn't understand much about vapor control, but we did want to positively pressurize. We wanted to bring outside air in and keep the outside air or keep the unconditioned air out of the space. And a lot of those envelopes over time have failed, as with positive pressure being one of the background causes. Where we're at today is recognizing that really the idea is that as long as we're not bringing the unconditioned air in, as long as, i.e., we're not negatively pressurized, we're pretty much okay. So we look for more of an equal recirculation control or recirculation operation where we're at equal or neutral pressure, if you will. And the key to this is that we send the same amount of air into the space as what we bring back out of it in terms of total volumes. So pressurization is still one of those areas that it can vary. It can vary in the application. If you have a particularly dirty or clean environment that you're either trying to keep out or that you're trying to keep in, pressurization can still be designed. But I think especially for storage environments, it's looking at it and thinking less about positive pressurization and more just about not letting unconditioned air into the space. And positive isn't necessarily required for that. We can work with neutral. Oftentimes we can get away with less outside air in that equation.
Great, thank you. Sorry, I think you were kind of petering out at the end there, so I'm not sure if I caught the last thing you said, but no worries.
Okay.
So I'm going to just jump to the next question we had from A.R. Mancuso, who was wondering if you might want to speak on MERV ratings for filtration. And so Tara did share a link there. I don't know if you saw that, Jeremy, of the
Sure.
airpurifierguide.org. But do you want to expand on that a little bit?
Sure. MERV ratings are a US standard for different levels of filtration, and basically it's looking at percentage efficiency for different for particle size type. And keep in mind that the US and the international standard, at least the European standard for filtration, are two different ratings. I don't remember the European numbers off the top of my head right now because I usually speak in terms of MERV. But if you are outside the US, look for your own applicable standard of filtration. In the United States, when we're talking about MERV ratings and filtration for particulates, which is what MERV addresses, the scale goes up to MERV 15, and at MERV 15 we are talking about clean environments, laboratory, very clean laboratory settings. This is beyond the range of HEPA filtration. HEPA filtration starts at about, give or take, 13 or so, 13 to 14, actually, I think it's 14. But for most environmental designs, practices and standards will vary. Pre-filters generally come in somewhere between a range of about MERV 8 to MERV 11, and those are designed primarily to look at taking out pollutants and particulates, everything ranging from different types of mold spores to pollens, pick your pick. And then usually for most systems, there will be a fine filter designed into the system as well after that rough filter. So we have a MERV 8 to start, and that fine filter afterwards is somewhere in the range typically of a MERV 13 to MERV 15. And this is something that's interesting because there have been a lot of discussions just recently on what these standards should be moving forward. Oftentimes what is recommended, at least on paper, is a MERV 15, which can be very expensive and very energy intensive. A lot of institutions will choose to install a MERV 13 filter instead. A little bit less total filtration, but for our purposes, typically sufficient. Storage environments are not meant to be pharmaceutical clean rooms. So for storage environments, a lot of institutions will go with a MERV 13 as a final filter. One of the things that this was a conversation I just had a few weeks ago with a gentleman who is a member of I'm totally forgetting the acronym now, but it is the National Filtration Association, whatever the right title for that is. And his comment to us in cultural heritage in particular when we were talking is that unfortunately, even though the standard in the testing is similar, in other words, a MERV 13 rating is a MERV 13 rating, long-term performance based on the product can vary significantly. In other words, the product that you buy that is labeled MERV 13 did pass for MERV 13 at some point in its testing. But it doesn't mean that it's going to hold up and continue providing MERV 13 over the life of the filter. And his comment was oftentimes with filtration, you get what you pay for, which essentially means that if you buy a cheap MERV 13 filter, don't expect it to actually perform at a MERV 13 level for a long period. That you might get an initial period of MERV 13 performance or good filtration performance that then tails off, and now you're not filtering as effectively as it was originally designed. So, it was an interesting discussion. I think there's a lot more for us to kind of ferret out in those regards in terms of thinking about what is the right approach for cultural heritage in general. The 15 recommendation is good as a starting point, but again, practicality oftentimes indicates that institutions simply can't afford that MERV 15 recommendation. But MERV 8 as a pre-filter is fairly common and generally accepted. In some applications, you may need to go to a MERV 11 depending on the downstream piece of equipment. And finally, that MERV 13 to MERV 15 is a typical fine filtration standard to achieve in terms of the equipment.
Great, thank you.
Thank you. Tara just put up the link there, National Air Filtration.
Yeah, I was just gonna.
As did John. Thanks.
I was just gonna point that out. Yeah, jumping in at the end there. Thanks, everyone. And apologies, I just made that.
It's a community. We're all working.
Yeah, exactly. It is a community. I accidentally made the survey link go away, but I'm bringing it back if anyone didn't get the chance to click on that yet. One moment, but we did have another couple of questions for you, Jeremy. Romana wants to know, what suggestions do you have for dealing with issues of spiking humidity due to outside air intakes? So extreme humidity and large amounts of rain are causing significant spikes in the 70-degree humidity range overnight for her institution. So,
So this is a case where, yeah, that's welcome to the world of no easy answer. But especially if you're looking at an overnight scenario, one of the things that I've often used with institutions in the past is to really look at your outside air control and what it is that you can do. In many cases, it's worth thinking about reducing your quantity of outside air brought into the building overnight, whether it's causing a problem or not, but really just to reduce that moisture load on the building and on the system. If you're in a particularly tough weather cycle right now, and I know I'm not sure where you're located, but I know in the East Coast, especially over the last month, Philly and New York have had a lot of problems with very high moisture contents. It's one of those situations that if you can get into your system controls, if you have this capability to dial back the outside air quantity overnight and reduce the moisture that's being brought into the building when you don't need the fresh air for occupation, that can give the system and the environment a little bit of a chance to catch up in terms of being able to dehumidify more effectively for that 8 or 10 or 12 hours, depending on your building schedule. And then recognizing that when the people are back in the building, you will certainly need to open up the outside air intake again for occupation. And you're going to reload the space when it comes to moisture, but it at least should give you some chance to recover during that overnight period. There's not That's the easiest, and I realize that isn't necessarily easy, but sometimes that's the easiest stance that you can take. You can get into looking to see whether or not there's any additional capacity into your cooling coil or into whatever system you're using for dehumidification, but chances are pretty likely that may be maxing out the capacity for dehumidification already. So it's really about minimizing the incoming load and minimizing outside air. And finally, the other thing just to keep in mind in those scenarios, um, how do I want to put this? Think carefully about what your environmental conditions are and what it is that you're seeing in terms of spikes. And I don't want to be casual about any of this, but do keep in mind that overnight spikes, if they only last for, let's say, 8 hours or so, where you momentarily pop up to the high 60s, or you might just breach over 70%. Sometimes those may not be as panic inducing as we would naturally think that they should be. They're not great for mechanical, especially for materials that are extremely sensitive or extremely um, reactive to moisture contents. But also looking at that from a mold perspective, it can take an awful long time at those low 70 conditions before you actually get into germination. So think carefully about how long these high RH periods are lasting and exactly what the risk might be. Because if it is only a weather event, I think conditions have started to get a little bit better in New York and in Philly the last few weeks. And I see Ramona, okay, you're in Jersey. Um, Once that weather pattern changes, the likelihood is that you'll get some better performance and you'll be back, if you will, out of the woods in terms of thinking about your moisture control. So, also think carefully about whether or not it's the time to panic or when that time to really take action is. If you think that there is the risk of specific damage being done in the environment. But otherwise, materials do take some time to equilibrate to moisture content, at least most materials. So these short-term fluctuations may not always have the impact initially
thank you. Yeah, I know a lot of us on the East Coast are probably looking forward to a break in this very rainy weather. So, we had another question here from Tara. She said that she encountered a desiccant wheel setup where they were using the heating coil to dry out the moisture on the wheel. She's been arguing that it needs to be superheated and the heating coil that exists in the AHU isn't sufficient. She's just wondering if she's right about that.
Right and wrong are very
Mm-hmm.
loaded terms. Um, let's put it this way. What I was talking about is an active desiccant design that is specifically meant for dehumidification. Just so everybody knows, there are other silica wheel designs out there that are meant for oftentimes energy transfer, or for lower levels of dehumidification than what we would often look at them for in collections environment settings. I don't want to speak to what the specific environment or the design of the system might be, Tara, but there are certainly applications where if the level or if the quantity of dehumidification is relatively minor in terms of what it is that they're trying to achieve, or if they're looking at a situation where it's actually an energy wheel that is being used to transfer heat energy from one part of the process to another, then oftentimes we won't see that superheated reactivation air process. We actually do just see this process where we're moving a little bit of heat from one side of the airstream to the other in order to help out in the right location. So wheels are not always going to be superheated depending on the application. There are scenarios where we could just use a standard heating coil, or oftentimes there might not even be a heating coil. It may just be the incoming outside or return air that is adding a little bit of heat to the surface of that wheel, then gets transferred back. It's kind of hard to talk through without a diagram, but there are a lot of heat transfer scenarios or designs where we're moving heat from the mixed air airstream over to the reheat side to save a little bit on mechanical. We basically bypass the heat around the cooling coil. So it's kind of hard to say right or wrong where you're at in that particular scenario or that particular situation. But just understand that there are a lot of different ways that these technologies get put into play. And depending on what the engineering design or the intent was, it may or may not be doing the right thing, or at least the thing that you want it to be.
And
But yeah, she just put a comment in there. Enthalpy wheels. Yes, those total energy wheels are also called enthalpy.
yeah, and I forgot to ask her follow-up questions about enthalpy wheels being the same as desiccant wheels are different applications. So, sorry, Sarah. Um, and let's see. I think we got pretty much all of the major questions through here. I just want to acknowledge Susan Lugo's down there in the U.S. Virgin Islands who said that this is such great and specific information. So many times the facilities manager is undervalued, and as in the case of a lot of Virgin Islands, libraries, archives, and museums are doesn't exist at all. Um, and just a call for facilities professionals to work hand in hand with librarians, archivists, and museum professionals. So here to that. Thank you, Susan. I think this community should be trying to advocate for those collaborations as much as possible. So let's see.
Well, and I want everybody to know just real quick, I'll just throw this out there, just briefly, that the collaborations do happen. I don't want anyone to feel as though that communication isn't there. It can be limited and challenging at the individual institutional perspective, but I will use the example right now that ASHRAE, the American Society for Heating, Refrigeration, and Air Conditioning Engineers, has a full chapter on how to design mechanical systems for museums, galleries, archives, and libraries. And that chapter gets edited, rewritten every so often. And we've gone back through just in the last 9 months or so. There's a committee, give or take, of about a dozen of us that have gone through and done some significant editing and rewriting of that chapter for ASHRAE. It's chapter 23. The new chapter will be published in 2019. But it incorporates a lot of the new preservation research, a lot of the new what we understand about operation and control, new design considerations from an equipment perspective and from maintenance perspectives, a lot of information on building envelopes that wasn't there previously. So this is really significant in terms of not only the new information that is being brought out there for the engineering community to consider and design, but I want to also put it out there as an example of how, at least at the science end, at least at that discussion from a strategy or from a standard perspective, that the discussion between the communities does occur. That the engineering world, the architecture world, the conservation science, and the preservation worlds, the communication is there. We think about it on a very kind of upper level, and it's a trick of oftentimes getting that to play out the way that we would really like it to on a day-to-day level in our individual institutions, and encouraging this teamwork, if you will, this integrated approach, this holistic approach between both the collections professionals as well as the facilities professionals. And that has changed an awful lot. A lot of people have made a lot of headway, had a lot of success, and it's something that as a field we just need to continue working at and improving that communication.
Jeremy, we've had a couple of calls for that link if you have that available.
Yep.
Um,
Anne and Susan for the ASHRAE information. Unfortunately, there's not a link that I can send you yet. It's right now in the final stages of being rewritten. It still has to go for submission to ASHRAE, and publication will be summer of 2019. So I think as long we're going to keep up these discussions, I want to make sure to get this information out to the different preservation and conservation communities among the allied professions. But that information will be coming available starting next summer. And Tara, your 2015 copy is now going to be significantly outdated in terms of content. A lot of that content is significantly changed.
well, I will echo Anne Frelson's comment of thank you for keeping our community in the loop about it. So appreciate that, Jeremy. And um, we're getting close to the top of the hour, so I think I'm going to go ahead and wrap things up here. But of course, I have to give a big thank you to Jeremy for once again sharing your words of wisdom. This is such valuable content, and it's very important for us in the field to keep up to date on all of this type of work. So thank you for that. Thank you to all of the participants. For those of you who are able to join us for the extra few minutes for questions, thanks for hanging out until the end. And for those of you watching the recording, thank you for checking out this content after the fact as well. I again want to give a shout out to the leadership of the AIC Emergency Committee for organizing these programs. Keep an eye out for future educational opportunities with that group. And I hope you all have a wonderful rest of your day.
Thanks a lot, everybody, for joining us. It's been my pleasure. Have a good one, and let's do it again sometime in the future. Thanks a lot. Bye.